Hi. So now that we've established a derivative test to find maximum and minimum, we can actually try to look at it from a different perspective, from a perspective of differentials. And look, this is what we're going to do right now. The differential versions of optimization conditions that we used before. We will need it in the future actually to explain how those conditions work in more general setting of functions with more variables that we're going to actually start since the next video. Okay, so look, before we jump into it, let's go back for a second to what is a differential. Okay, so we are again dealing with function y equals f of x. We already said a couple of things about differentials, but maybe now let's practice them a little bit and let's say a little bit more. Okay, so for this function, y equals f of x, so function of just one variable, I can calculate derivative dy dx. Okay, and I can be 100% sure that this derivative dy dx is equal to the same derivative dy dx. And look, what did we say before about it? I can, for example, multiply both sides by dx. And what am I going to get? That dy is equal to dy dx dx. Okay, so what is this all about over here? Here we see that very small change in y can be written as very small change in x times derivative of y times x. Okay, look, so as we said before, let's write it a little bit differently. Of course, this is the same as dy equals f prime of x dx. Right? This is the one version that we're going to use. So let's write it down this way. Okay, so what do we have over here? If y is a function of x, it means that x is determining the value of y. And look, if x is changing by some very, very small amount, maybe let's write it like this. Function f translates x into y. Now, if x is changing by an extremely, extremely small amount, by how much is y going to change? Well, of course we know it's going to be dy, which is again an extremely, extremely small number. But now the question is, what links those two? And look, the link between those we get from the expression of the differential. So this incredibly tiny change in y, and it is given by f prime. So the derivative of f of x. And look, as we said before, those changes are incredibly tiny. So why does it really matter by how much y is changing? So because it's so very little that actually doesn't make a dent, right? If this is extremely tiny, infinitesimally small, this also is going to be infinitesimally small. So why does it matter? Because look, very often we are not interested in what is the size of dy. We are rather interested in what is the sign of dy. Whether dy is positive, so whether we are going up, or whether dy is negative, so are we going down. And look, this information is conveyed in the derivative. And look, because we can do this at one given point, we can repeat it for every other point. And this is basically why we have the derivative. Because derivative function is giving us this information for every point of the function at which this function can be differential. Okay, now let's do maybe a couple of examples of calculations of differentials, which are, to be perfectly honest, extremely tricky. Okay, so look, if we have y equals 2 minus x squared, then what is dy? dy is going to be derivative of this function, in our case, negative 2x times dx. What if the function is y equals 1 over x? We remember that 1 over x is the same as x to the power negative 1. What is dy now? dy is equal to minus x to the power negative 2 dx. Okay, so let's try another one. What if y is equal to ln x? Well, if y is equal to ln x, then dy is equal to derivative of this 1 over x times dx. And look, because it looks like that, in this case, we can write it shorter. We can write it, for example, as dx divided by x. It's still the same expression. Okay. Now, also one very interesting case is y equals to e to the power of x. Then, dy is equal to e to the power of x dx. And look, basically what I wanted to show you in those examples is that once you know how to calculate derivatives, calculating differentials is very, very easy. Okay, so now that we reminded ourselves what are differentials, how do they work, and how to calculate them, now let's figure out how we can use them to replace our optimization conditions that we've used previously. Okay, and look, so again, remember, we've got a function y equals f of x. Now, for this function, first order condition for finding maximum or minimum is that f prime of x, so first derivative of this function, is equal to 0. Now, how can we translate it into a differential condition? Look, it's actually not that much, not that complicated, but it's better to see it when we have a graph. And I'm going to give you this on the example of minimum, but as you will see, the example for maximum works exactly the same. So here we have some x, here we have y, and let's just say that the function looks like this. Okay, so look, we clearly see that the bottom over here is clearly a minimum. And look, what do we know about, so specific about the minimum? Well, we know that the slope of the function at the bottom is equal to exactly 0. So basically we've got a flat line that is parallel to the horizontal so knowing this, of course, this is how we were using derivatives, right? The slope of the function at a given point, x0, and if we would have x0, must be equal to 0. Okay, but we also said that there are some very interesting things happening on both sides. Look, because if I would be drawing a tangent line for every point in the neighborhood of this point, of course, imagine, I cannot do it over here because it would be invisible, but what I wanted to show you is imagine that this is very close, because it will work exactly in the same way. We see that over here, we have a situation that the tangent line is downward sloping, right? So, on the right hand side, of the minimum, we've got a situation that is a little different, right? Because here, the tangent line is going to be upward sloping, right? So, what we can actually see from here is that every time if I'm going to be drawing a tangent line, here it will be downward sloping, but it's going to, as I'm getting closer and closer to minimum, it's going to get flatter, flatter, and flatter, and flatter. It's going to reach value of 0, and of course, the next thing after 0 would be some very tiny positive value, so that line would be getting steeper and steeper and steeper and steeper. And this is still exactly what we said, and this is exactly what we said when we were talking about using derivatives. So, what can we do here in case of differentials? Okay, look, of course I cannot draw you here a differential, you know, because it's so tiny. But we can, I can show you how to calculate it, right, using derivative. Look, imagine that we are starting, let's just say at some point like this. Think of it as an approximation, of course, because dx is very, very tiny, right? So, look, over here, maybe over here, we're going to have some dx. Okay, and over here, well, of course, remember, we are imagining that they are extremely tiny, but then you would not be able to see it. What do we have here? Here we have dy, right? Again, look, how do I get from dx to dy? Well, I'm using the slope of this function, right? But look, the more important thing here for us at this moment is to notice, sorry, I need to find more colors. Okay, we used blue, then I think I have orange and purple. Okay, what can we say here about the sign of dx? Well, the sign of dx here is positive. What do I mean by that? It means we moved in the right direction, right? From left to the right. So dx is a positive number. Now, what can I say about the sign of dy? Well, this sign is negative. How do I know? Because we moved from the higher value to lower value. Well, of course, by very little, but look, definitely dy here is negative, and dx here is positive. And look, what does it mean? As long as dx here is positive, every value to the left of dy is going to be negative because we are going lower and lower and lower and lower. Now, what is happening to the right of our minimum? Well, the opposite. Well, the same thing happens to dx. Well, dx here is again positive, right? We clearly see that we again move from left to right. But what happened to dy? Well, dy now went from here to some point a little bit high. Of course, remember, those should be extremely tiny, but I wouldn't be able to draw anything. So look, what we can say about dy over here is that dy is positive because we basically moved from lower value to some higher value. Okay, so I hope now you can see some resemblance between what we were observing in terms of derivatives and what we observe in terms of differentials. Here, the slope of the function is negative, so dy is everywhere here going to be negative. Over here, dy is positive. The slope of the function is positive, so dy is going to be positive, of course, as long as dx is positive. So we are moving from left to right, from lower values to higher values. And this is actually the direction in which we are going. Okay, so what is happening at this point? Okay, look, first order condition in terms of derivatives look like this. Now, differential looks like this. So, if those two are apparently the same, because here we have derivative and here we have derivative, at our specific point, let's now call it x0, then apparently what must be happening here is that dy is going to be equal to 0. How do we know that? Well, doesn't matter what is the value of dx, and actually we know that dx is positive. The value of derivative is 0, and because it is 0, dy must be 0. And look, this is a situation that happens only at one specific point. Over here, dy is equal exactly to 0. So basically, if we want to translate first order condition from derivatives to differentials, we get that dy at some specific point, x0, must be equal to 0. And this point is going to be either minimum, but of course we could repeat exactly the same graphical representation for maximum. Okay, so look, what we've done at this very moment is that we translated from differential condition, from condition based on derivatives to condition based on differential. But you see that there needs to be exactly the same, in the sense that they give us exactly the same location of the point. Okay, but look, again, this is the first order condition, and we, at this point, we cannot say whether this is a maximum, a minimum, or even, inflection point. But, of course, for that, we need to use second order condition. But before we can move to second order condition translation to derivatives, we need to do one more thing. We need to calculate second differential. And look, I'm going to show you this in two different ways. Okay, first, differential d squared y, so second differential, is going to be a first differential of the first differential. Well, not complicated, right? Now, so we already calculated the first differential, and we know that this is equal to f prime of x times dx. Okay, and look, every time when we calculate the differential, we go through exactly the same process. We are differentiating, we have function y equals f of x. So, what is the first component? Look, over here, the function got differentiated. Now, we need to differentiate this function. So, here we will have a second derivative. And now, look, this dx is going to stay because we had it before. But now, we need to introduce another dx. And to simplify this, because we have dx, why not write it as f b's of x dx squared. Okay, so look, what we are getting from this is that differential d squared y is equal to f b's of x dx squared. But, look, again, I could use a different way of doing it. Second derivative, d squared y dx squared is equal to d squared y dx squared. Right? So, look, now if I multiply both sides by dx squared, what am I going to get? D squared y is equal to d squared y times dx squared times dx squared. But isn't this just the same thing as over here? So d squared y equals f b's of x d squared x. So look, this is how we approach this when we calculate this. We can also get it again just from the definitions of the derivatives as ratios of differentials. Okay, so now that we know how to calculate the differential, differential, let's think for a second about potential values. Okay, look, we clearly see, okay, let me just write it so it's more clear. That we've got the d squared y is equal to f b of x dx squared. Now, in this case, actually one thing makes everything here very simple. Because dx, on one hand, could be positive or negative, right? We don't need to just move from left to the right, we can move in both directions, right? But it doesn't really matter in case of dx squared, because 2 times positive value is positive, 2 times negative value is negative. This is definitely going to be higher than 0 because we assume that dx is different than 0. Just slightly, but different. Okay, so now what would be, so how can we use what we've learned thus far to find second order conditions using differentials? Okay, look, again, let's start with second order conditions for derivatives. Second order condition says that if f b of x is bigger than 0, this must be a minimum. If f b of x is lower than 0, this must be a maximum. Okay, but if this is the case, then again, probably we can deduce the connection. And look, the connection here is straightforward. This part of the second differential is definitely positive, right? So, again, the value of d squared y, again, solely depends on the value of the second derivative this time. And this is how we obtain second order conditions in forms of differentials. So, get the d squared y is equal to f, which is equal to f b of x dx squared. And if this is positive, this must be a minimum. On the other hand, if d squared y equal to f b x dx squared is lower than 0, this is a maximum. And now we've obtained everything we want. First order condition in terms of differentials is that dy must be equal to 0. The second order condition is that if d squared y is positive at the point x0, of course, here, we will have minimum. If it's negative, we will have maximum. And again, now, you could say, okay, but why do we need this? If we already have those conditions. Look, the thing is, we don't. And I would never ask you to calculate, to find maximum or minimum using differential conditions. But the situation is not as easy when we move to functions of when y or z is a function of x and y, or y is a function of x1, x2, x3, and xn. Then things are getting very complicated very fast. And using differentials then is going to make our jobs way easier. But as you will see, it will lead us back again to derivatives. Okay, thank you for your attention. And since the next video, we're going to start three-dimensional functions and functions of more variables. So, for example, we're going to start with z equals to f of xy, but then we're going to move to more complex case of y equal to f of x1, f of x2, f of x3, until f of xn. We will learn how those functions look, and for all of these functions, we will learn how to find their maximum or minimum if it exists. Okay, thank you for your attention and see you in the next